So now we have a slightly different kind of polymerization, because we have a carboxylic acid and we have an amine rather than an alcohol. But again, we can condense them together. So the usual thing, you lose the OH group from the carboxylic acid and one of the hydrogens from the NH2, which will condense out to form water. And if you do that visually, it makes it obvious what's going to happen, which is that you're going to get that left from the carboxylic acid group, and then the NH left from here. And then at the other end the same thing, because obviously the chain is going to continue, so this NH2 again just becomes NH and has a linker bond which will be to the carbonyl of the next residue on that side, and similarly here that carboxylic acid becomes just C double bond O with a linker to the next NH. So that's the repeat unit of your new polymer, and that is a polyamide rather than a polyester. And it's called a polyamide simply because that group in the middle, which forms the link, is an amide group, or specifically a secondary amide group, because the nitrogen is attached to 2 carbons, so it's a secondary amide group. So then it wants to know, well, could you make that alternatively using an acyl chloride rather than a carboxylic acid? And as we know, the answer is yes, you can. And not only can you do it, but it works much better. So the only difference is simply that instead of having the COOH there, you have COCl. And so you have the acyl chloride group at each end there. And as we can see, what happens is that you condense out HCl rather than H2O, but you get exactly the same repeat unit, and the advantage is that the reaction goes much more straightforwardly. Okay, so now we're back with another polyamide. This is question 7, but you can see this is a different sort of polyamide than we had in the last question, because where in question 6 we had this pattern, where we had a pair of NHs separated just by a bunch of carbons, followed by a pair of carbonyl groups separated by a bunch of carbons. So we got that kind of pattern. We don't have that here. So this is what you get when you have a diamine condensing with a dicarboxylic acid, which is one of the ways to make a polyamide. But this one, you can see we don't have that, because instead, if we follow it through, we start here, we have an NH and then a carbonyl after this carbon, and then NH, carbon, carbonyl. So we don't have that pair of carbonyls just separated by carbons, or pair of NHs. And so the repeat unit this time is actually much simpler. It's just that, because you can see you just have NH, a carbon, and then a carbonyl, NH, carbon, and carbonyl repeated there. So that's the repeat unit, and that means that the monomer is just this. Sorry, get that the right way around. Okay, so the monomer is just that. And you can see if you just condense lots of those together, then you get the usual pattern. You'll lose the OH from here, hydrogen from there, and they'll condense to make that unit. So that's the monomer. The type of compound that is, you hopefully recognise, is an alpha amino acid, because you've got a carbon attached to both an amino group and to a carboxylic acid. So if they're attached to the same carbon, that's an alpha amino acid. And it then asks you what happens if you hydrolyze this polymer. The polymer, you probably know, is a polypeptide or a protein, other biological words for it. So these are very important polymers in biochemistry. So we've got to write an equation for the hydrolysis. So that means we've got to start by writing this in the format of repeat unit, with an N to illustrate the fact that there's lots of them. So we'll copy down the repeat unit like that, stick it in the bracket, and say that's repeated n times. So that's the formula for the polymer. And it's going to react with n lots of water, because it's just the reverse of the reaction that makes the polymer. That's the important thing about hydrolysis. And this applies both for polyesters and for polyamides, that the hydrolysis is just the reverse of the condensation of the carboxylic acid with alcohol or amine. So just as the condensation produces water, so the hydrolysis needs water. So that's going to be the reaction. And that would produce, if it just reacted with water, the original alpha amino acid, which is NH2 there, and then COOH here. And that would be the equation for, and we need n lots of that, of course, because we've got n of them here. That would be the equation if it didn't specify alkaline hydrolysis. It would, for example, be the equation under neutral conditions, as might occur if it was an enzyme catalyzed hydrolysis, for example. But because it says alkaline hydrolysis, we have to think, well, what would be different in the product as a result of the change in pH, and then we need to reflect that in the way we balance it on the left-hand side. And of course what's different is that under alkaline conditions the amino group's no different. That's not acidic, so it's not going to react with alkali, but the carboxylic acid group is, and so that will become O-. And since we're reacting with sodium hydroxide, we can write it more specifically as O- Na+. And of course that's now not going to balance unless we change it on this side, and the way it changes is simply that it reacts with sodium hydroxide rather than with water, and that then gives the correct balancing. So that's the equation for alkaline hydrolysis. So the way to do it, again, unless you're very confident, is write it first for the equation, just reacting with water to make the amino acid, and then change it and think, right, what's going to change as a result of it being alkaline? Do that on the right hand side and do what you need to do to make it then balance on the left hand side. So then the last bit, it asks you to do the same thing with acidic conditions. So let's restore the equation to its original water form. So we have NH2O there, and that goes back to being OH. And then say this time, well, what will be different because we're hydrolyzing it by refluxing with hydrochloric acid? So again, we look at each group and say, well, what happens to it? Carboxylic acid group makes no difference. You can't add an extra proton onto that, so the acid does nothing to it. But of course it can protonate that, and that's the difference. So instead of being NH2, it becomes NH3+, which we can write like that, and it will be Cl- because it's hydrochloric acid that's been reacting with it. And to make that balance, you can see all we did was add an extra H+ and Cl- onto this side, so we just need to add NHCl onto that side to make it balance. So hydrolysis reactions are relatively simple, but the trick is to check out the conditions, because you need to tweak them slightly to make sure that if it's under acid conditions, you protonate the amino group, which needs an extra acid contribution on the left-hand side. If it's under alkaline conditions, you need to deprotonate the carboxylic acid, and that means it ends up being a reaction with hydroxide rather than with water.